Okay, we're going to start our new unit. It is the waves unit. And a wave is anything that can transfer energy. So waves transfer only energy. And there are different characteristics of waves that I just want to first define for you. So I'm going to draw an equilibrium line. And on that equilibrium line, I'm going to draw a wave. This is one of the benefits to having grid lines on your paper. And let's say I want to end it like that. So here I have a waveform, and I really should make sure you can see my full wave, because if you can't, it's going to complicate things. Okay. So here's my wave. And this wave that I've drawn has many cycles on it. So the first thing I want to do is I want to define the term wavelength. And wavelength is represented by variable lambda, so it's a Greek letter. So anytime we're referring to wavelength, we're just talking about the length of one cycle. So this would be 1 lambda. So how many wave cycles then are on here? Well, we have 1 wave cycle, 2, 3, 4.5. So in this diagram, we've shown that we actually have 4.5 lambda depicted. So let's just write down our definition of wavelength, which is simply the length of one wave cycle. One full wave cycle. And we measure the wavelength in meters. So now if right here what I have are 4.5 lambda, or 4.5 waves, then what would one wavelength be if I tell you that from here to here we have a distance of, let's say, 45 meters? Then what would 1 lambda be equal to? So in order to solve for the wavelength, so find the wavelength on the above diagram. So we want to know the length of just one particular wave. So if we have 4.5 lambda and we have 45 meters, then 1 lambda is going to be equal to this total distance, 45 meters, divided by the number of waves that we have shown, 4.5. So obviously here we're going to have that lambda is equal to 10 meters. Meaning that each of these waveforms is 10 meters long. Okay, so right now, by the way, we're talking about the characteristics of a wave, and the first one is wavelength. So let's just write this down, characteristics of a wave. So the first one is wavelength. Okay, and by the way, we said that a wavelength is the length of one full wave cycle. But I want to just talk about what characterizes one full wave cycle. So how do we define one wave cycle? Well, one full wave cycle is going to be associated with 360 degrees. So I want to just go through this diagram and show you what I mean by 360 degrees. One full wave cycle, you can think of it as one sinusoidal wave, which really is just a circle cut in half. We know a circle is 360 degrees, so if we were to superimpose these two points, we would have a full circle. So one full wavelength is represented by a total of 360 degrees. What that means is we can actually break this waveform into degrees. So here we have 0 degrees. Halfway through here we have 90 degrees. All the way back to the equilibrium point we have 180 degrees. Down halfway through here we have 270 degrees. And over here we have 360. We've made our full complete circle, if we were to superimpose these two parts of the waveform. Okay, so just know that you can actually divide this structure into degrees, and that's going to help us a lot later on. Okay, characteristics of a wave. The second one I want to talk about is the amplitude. And the amplitude is simply the distance, or I should say, let's say the maximum distance from the equilibrium point. So again, our line here is our equilibrium line. So our amplitude is in reference to this line. So we can measure our amplitude from the equilibrium line to the highest point, which we're going to name in a second, or from the equilibrium line to the lowest point. That distance is going to be our amplitude. So on the diagram that we've shown here, if I were to tell you that the distance from the highest point on the waveform to the lowest point is 2 meters, then our amplitude is going to be half of that, because again, we're only measuring from the equilibrium line. So in the diagram shown, there's an amplitude of 1 meter. And this amplitude is reflective of how much energy the wave has. So the higher the amplitude is, the more energy that's being transferred. So greater amplitude is associated with more energy. And this is really true for mechanical waves. True for mechanical waves. Okay, so for example, if you were to make waves in a pool, that's a mechanical wave. So waves in a pool, but also sound waves. Okay, and we'll talk more about those a little bit later. This isn't going to be so true for electromagnetic waves, but we will come back to that in a little bit. Okay, so I said that I was going to define the highest point on a wave. I will also define the lowest point on a wave. So our third and fourth characteristics of a wave are going to be the crest, which is the highest point on a wave, highest point of displacement. So that's just a name for this position right here, so that is our crest. Okay, and the fourth characteristic is a trough. That is our lowest point. And that would be right down here. This is a trough.